So we're trying this one again, and just explain everything kind of crashed. So I'm trying again, and I'm taking it slow. Maybe I'm gonna make shorter videos. So maybe what I'll do is I will try and keep these videos concise. There are 11 problems in this paper too, so maybe I'll do in 1 through 4, 5 through 8, and 9 through 11. Anyway, so we have Compton scattering. X-ray photon interacts with a free stationary electron. Electron recoils with energy 500 eVs. We have the wavelength of the scattered photon. What is the energy of the scattered photon? So energy will be conserved, so the total energy of the photon coming in plus 0, because the electron's at rest, is equal to the photon that is scattered plus the kinetic energy of the electron that gets knocked away. So to do 1a, we don't actually need the total energy expression. I was just kind of explaining the Compton scattering, but we do know the wavelength of the scattered photon, so we can get the energy from hc over lambda and then convert that to eVs. So we get 2.55 times 10 to the negative 15 joules. We convert that to electron volts and get 15,937.5, which is close to 16 keV and agrees with the mark scheme. Next question. Find the wavelength of the incident photon. This is where the energy balance that I mentioned before comes into play. So we have hc over lambda for the incident photon plus 0 for the electron at rest equals hc over lambda for the scattered photon plus the scattered energy of the electron, which we have. Since h, Planck's constant, is in joules seconds, I'm going to have to convert from eVs to joules. We get 7.56 times 10 to the negative 11 meters, which agrees with the mark scheme. Next. 1c says, why do the results of the experiment were they inconsistent with wave model of electromagnetic radiation? Or in other words, how is Compton scattering an example of light as a particle, and the wavelength of the X-rays changes from 7.8 times 10 to the negative 11 to 7.56 times 10 to the negative 11, which makes sense from energy and from a particle perspective, because the energy of the photon is transferred to the electron as a result of the collision, so the photon after the collision loses energy, therefore has a longer wavelength, and oops, that's 7.56 to 7.8, let me fix that. There's a loss of energy, so wavelength goes up, but according to the wave model, wavelength should stay the same. D is calculate the scattering angle. I'm going to need the Compton scattering equation for that. Now I have no blessed idea where they're getting 1.24 times 10 to the negative 6 and 0.511 times 10 to the positive 6. How they're substituting that for h over MEC. Here's what I have. There's h, mass of the electron, and the speed of light. So when I throw those together, throwing those numbers in, and then solving for cosine of theta, we wind up with is 0.010679. And then if I inverse cosine that, I get 89 degrees, which agrees with the mark scheme. Giddy up. That's number 1. Number 2. So we have electrons going on a crystalline sample of graphite. Electrons emerge from the sample and form a pattern on the screen. There's a series of bright and dark rings, like fringes, concentric with the direction of the incident beam. Why is that evidence for matter waves? Because we're talking about electrons here for matter. And why is it evidence of waves? Because of a diffraction pattern. Diffraction is a property of waves only, and the pattern that is formed is an interference pattern. So if you remember the interference pattern that you get from a slit, so you remember that the kind of patterns that appear on a screen, imagine the same thing as a set of concentric circles, and that's what they're talking about. 2b says beam is produced by accelerating electrons through a potential difference U. Typical interatomic distance in the graphite crystal is 2 times 10 to the negative 10 meters. What's the minimum value of the potential difference for the pattern to be formed on the screen? 4 points. All right, 4 marks. So here's a couple things going on here. Let's go to the next page. Page breaks. Okay, so first of all, it says the Bernoulli wavelength of the electron should be comparable to or shorter than the interatomic distance. Why is that? And that's true because diffraction occurs when the wavelength is close to the gap size. So if the wavelength, the de Broglie wavelength should be close to that quote-unquote gap size of 2 times 10 to the negative 10 meters. So there's a couple of steps here, but we pretty much want to solve for U, or the voltage, and show that it's about 40 volts. So we know that the energy of electrons is QV. I'm going to sub in E for the charge of an electron for Q, and U for V, since they're using U. We know that energy is momentum squared over 2 times the mass of the electron, P squared over 2m, for any particle. And however, we're talking about de Broglie wavelength, and remembering that de Broglie wavelength is h over p, therefore p is h over lambda. So when we break it all down and solve for u, we get h squared over 2 times the mass of the electron times lambda squared times e. I hope, we're assuming I did my math right. We're about to find out. Also, E is going to be in coulombs, since we're dealing with coulombs in joules, since H is in joule seconds. And don't be a knucklehead like myself and forget to square. And we get 37.6963, which rounds to 40 when you only have one significant figure, which the wavelength was to one significant figure, so that fits. So that works. My math was right. All right, C. Okay, so for C, we're comparing electrons to protons. It says protons can also be accelerated by the same potential difference U. Compare the de Broglie wavelength of the protons to the electrons. So E is QV, energy is QV. They have the same Q, it's one elementary charge, and the same voltage, so they're going to have the same energy. But energy is also momentum squared over 2m, and momentum is h over lambda. We established that before. So if we solve for the de Broglie wavelength in terms of mass and energy, we get de Broglie wavelength is square root radical h squared over 2me. So the energy is the same, and h is a constant, as is 2, but the masses are different. So the proton has more mass, and so since wavelength is proportional to radical 1 over the mass, as mass increases, the wavelength is going to decrease. So since the protons have more mass, they will therefore have a shorter de Broglie wavelength, which is exactly what the mark scheme says. They said we did need calculation. I kind of threw in the equations just to explain what the heck I was talking about. And that was number 2. So that was, we're halfway through this video. The goal is 15 minutes. Let's see if we can get there. 3a, I think that the mark scheme explains it. What's the de Broglie hypothesis? Is that a moving particle has wave properties, and that's a moving particle. It has to have momentum, by the way. So a particle at rest does not have wave properties. But then, so the de Broglie wavelength is Planck constant divided by the momentum, which is the equation from the data booklet. Like they said, don't just write the equation down, make sure that you define things through, explain what they are. So we have electrons being accelerated by 500 volts. So the energy of the electrons is their charge times the voltage. We'll put in E for the charge of the electron, equals 1/2 mv squared. When we solve for V, we get radical 2 times the charge times the voltage divided by the mass. Throw the numbers in, and you wind up with 1.33 times 10 to the 7 meters per second, which agrees with the mark scheme. I'm not really sure that's an E2 question, but it's still good to do. Okay, so passing through the holes, electrons strike the screen, whether the apparatus can show that the electrons have wave properties. So in other words, will the electrons diffract? And they'll only diffract if the size of the hole is close to the de Broglie wavelength of the electrons. So we had to figure out the de Broglie wavelength of the electrons. So I know that de Broglie wavelength is h over p, p is mv, and v, speed, we just got in B. It's radical 2 times the charge times the voltage divided by the mass. I could probably simplify this expression, but I don't know. I'm just going to throw the numbers in and see what I get. So when I run that calculation, I get 5.49154 times 10 to the negative 11 meters. Now that right there is like half the size of the atom of hydrogen, which is fine for the size of the particle, but it's not fine for the size of the hole. So no, the hole is not going to cause the electrons to diffract, because you would need, like, that hole is too big. In order to get the diffraction, you would need a hole smaller than a hydrogen atom. That is not happening. And that's what the mark scheme says. Mark scheme. All right, number 4. I have 5 minutes. 4a is pretty basic. It says h over MEC is the Compton wavelength. Show that that's 2.4 picometers. Run the numbers, and yes, you get 2.43 times 10 to the negative 12 meters. B. Photon with a wavelength of 6 picometers interacts with a stationary electron. That's going to be a Compton situation. After the interaction, the photon's wavelength is changed by 2.43 picometers, the Compton wavelength. State the wavelength of the photon after the interaction. So we have BI, state the wavelength after the interaction, and the wavelength is going to be greater because after the collision, energy is lost to the electron, and so if energy goes down, wavelength goes up because they're inversely proportional. So 6 meters plus 2.43, 6 picometers plus 2.43 picometers is 8.43 picometers. And BII, why did the wavelength change? I just said that. It was an energy loss from the collision, so the wavelength gets bigger. Energy is inversely proportional to wavelength. And the photon transfers some of its energy to the electron, so if the energy goes down, the wavelength increases. I just said that. All right. BII, deduce the scattering angle. So note from the problem that the change in wavelength was 2.43 picometers, which they defined as the Compton wavelength, which is h over mass of the electron times c. So we know that the Compton equation is change in wavelength is h over MEC, 1 minus cosine theta, but since those guys are equal, they divide out, and we wind up with 1 equals 1 minus cosine theta, therefore theta has to be 90 degrees because cosine of theta is 0. And then we have B4 BIV, in determine in joules the kinetic energy of the electron after the interaction. So the energy balance, we have E photon plus 0 for the electron at rest is E photon prime plus the energy of the electron prime. And E is hc over lambda, so basically the energy of the electron is the difference in the photons, hc over lambda minus hc over lambda prime, or hc minus the difference in the fractions. And so that's where this expression comes from right here, hc times the difference in the fractions. I kind of wrote in an intermediate step for the fractions, and you wind up getting 9.6 times 10 to the negative 15. 10 to the negative 15 is femto, so that's 9.6 femtojoules, which agrees with the mark scheme. And that was number 4. We'll continue in the next video. We are under 15 minutes. Here's hoping this works.